Good morning, class, and welcome to this lesson on Electrostatics 9 equipotential surfaces or equal potential surfaces. Today, we will be able to define an equal potential surface and describe how charges move between equal potential surfaces. So, the first thing I want to tell you is that um, an equal potential surface is kind of like a topographic map. On a topographic map, you have lines. Okay, this is a 2D version. This is a kind of like a 2D version of a map. You have these lines, and everywhere along this line is, say, 30 meters above sea level, 20 meters above sea level, 10 meters above sea level. So everywhere on this line is the same elevation. So this line represents hills, as you can see from these hills down here. So if you look at this 30-meter line, this whole line going all the way across is representative of this ring going around the mountain right here. Everywhere on this line is 30 meters. So it's kind of like equidistant. Everywhere on this line is the same distance above sea level. Well, an equal potential surface is everywhere along this surface is the same potential. Everywhere along the surface is the same potential. So if we did V equals KQ over R for our potential due to a point charge, we would find that everywhere along this surface right here would be the same potential. Everywhere along this surface right here would be the same potential because they all have the same radius with the same charge. So here's the same picture right here. So our first characteristic of an equal potential surface is the electric force. The electric force does no work. Electric force does no work on a charge to move along the surface. So if we remember, work or energy is equal to negative delta V over Q. This means work is done in between. There has to be a difference in potential for work to be done. And so if a charge is moving just along this surface right here, there is no change in voltage because the potential is the same. So because of that, no work is done on a charge on a surface. It has to be between surfaces. And so if we move from this surface to point A, this surface to point B, or this surface to point C, it's all going to be the same work done due to the fact that the potential, delta V, is the same for all of them. So that's our first characteristic of an equal potential surface. Okay. Our next characteristic, these red lines here. Here's our equal potential surface again. These red lines are all perpendicular to the equal potential surface. Okay, and these are let me add this electric field lines are all perpendicular to the surface. So they're always going to point perpendicular to the surface, and they're always going to point. They're always going to point in the direction of decreasing potential. They're always going to point in the direction of decreasing potential. So this is a higher potential, this is lower potential, they're going to be pointing outward. If we had a negative charge with circles around it, negative charge, the lines would be pointing inward, perpendicular to the surface. And so if we had a positive test charge, a positive test charge, as we know, is going to move from higher to lower potential. It's going to move from higher to lower potential. So if this was the case right here, it would move away from the center. If we had a negative test charge, and this is stuff we've gone over already, a negative test charge would move from lower to higher potential. So a negative test charge would move, if this is the same surface right here, a negative test charge would move inward. Okay? And that should be a little bit of a review for you. So here's a picture right here of a positive charge and a negative charge. And you can see here that all of these surfaces, these circles, these lines, these are all equipotential surfaces. These are all equipotential surfaces. Okay, and you can see they change as you move out further away from these charges. Okay, but they still are all the same potential as you move out. And even they have a weird shape at every single point. I'll pick this one right here. At every single point when the potential surface, the electric field line and the surface are all perpendicular. So I'm drawing perpendicular lines right here. So that's one of our characteristics. Perpendicular, the electric field lines are perpendicular to the surface, and they always point out from decreasing potential. And that's why you can see the difference here. On the negative side, they're pointing in, and on the positive side, they're pointing out. And so for practical purposes, what we're going to see here is we're going to get graphs like this on, like, say, an exam. And on this graph, you see all these different points: F, G, E, D, B, A, C. And so this is an equipotential graph, or equipotential lines. And on these graphs, the questions are going to be asked of, like, what is the difference in energy to move from B to C? And if you know that they're on the same line, you know there's no energy difference here. There's no work done to move from B to C. If you're asked to move from B to D, and you know the charge, you know the work done is going to be Q, whatever the Q is, delta V. And in this case, um, it would be -10. Oh, I forgot the negative there. I'm sorry. -10 minus +10. Because this one's -10, this one's +10. So you can actually calculate the amount of work done to move from one spot to another. Other common questions you might see based on this equipotential graph right here is the electric field stronger at I or H? Is the electric field stronger at I or H? Here or here? And the electric field is going to be stronger. If you just look at the picture, the electric field is going to be stronger at areas where the slope is steeper. So when the lines are close together, we have a strong electric field. And when the lines are further apart, we have a weaker electric field. And I'm kind of going out of order here, but what you're going to see here is we're going to have this equation right here, V equals E times D. I'm actually going to derive this and show you where this comes in the next video, but preview, this is going to be our equation. And so our electric field is based on the potential over the distance. And so if the distance in between the potential surfaces is less, we're going to get a stronger electric field. Okay? So those are common questions that you're going to see with equipotential surfaces in this chapter.